All right, hi everybody. We're going to pick up with our next lecture. Today we're going to be talking about some more measures of chaos and some interesting things that we introduced into to you last time. So I hope that you've been finding this interesting thus far as you continue to ask questions about what we're doing. That then helps us to shape even the lectures and the information that we are sharing. Chaos is a very broad type of field. It can find itself impacting a lot of different areas. We're trying to look at some of the basic principles, some of the basic characteristics and features of chaotic processes, chaotic oscillations, whatever you might call it. We're doing all of that. So you have a foundation, and then when you see it, then you will recognize it. Now, probably a little later in the course, I'll tell you a story about how I first encountered chaos and how I recognized it based upon conversations I had with a colleague prior, and that kind of started me on my journey of um, um, exploring, investigating chaos, and then also trying to find uses, applications, if you will, for it. And that's the basis here. So you will know it when you see it. You'll know about some of these characteristics and features, and you'll be able to talk intelligently about it and impress your friends at parties when we can have them again. Now, so for the last time we talked about conditions for chaos. We said that chaos requires nonlinearity. It requires feedback. It requires stretching and folding and a fractal state space. Now, what you'll find is that all of these conditions that I've just mentioned are related. And as we get more into three-dimensional type of chaotic flows, you'll see that more. But the nonlinearity causes the expansion, or has the potential for expansion. Feedback allows things to come back onto itself, so therefore the stretching and the folding are connected to the nonlinearity and the feedback. And then the fractal state space uh, is necessary, because if you ever had a trajectory, a flow in state space that fed right back to the same point, then it would then be a periodic system. So it can never really go back to any other point that has been visited. Otherwise, you'll have periodicity and it won't be chaotic, at least not over a long period of time. And so also too, this has to be bound within some fixed state space, which is what you see. So there are uses in technology. We'll begin to explore some of those. There are things in nature. Um, Fractals, they are objects of fractional dimension, and we're going today talk about how to calculate the dimension of a fractal, and you can see them in nature. And I invite you to look into the reading and even expand beyond that. Do some searches. Once you do searches on fractals, you'll be inundated with all kind of beautiful things. I encourage you to look at that. Now, a couple of things I want to go back and talk about with linearity. Well, first of all, I need to correct something. Last time I said that a linear system. So let's just say that we have, well, let's start it with this. Let's say that y equals f of x, where it looks like this, right? You have your input X and your output Y, and F is what governs. That's what's inside the box. Now, I said for linearity, this function must have, X must not vary. I said order plus and minus 1, but that's wrong. I need the red for that. Wrong. Okay, the order should be just x1, right? Because x to the minus 1 is equal to 1 over x, and that is not linear as you go through, right? If x, and as you go higher and higher in x, you see 1 over x, so it's going to start off at 0, which is undefined, so it's going to, and it's going to go to, as x gets bigger and bigger and bigger, it's going to go to 0, so this is something that looks like that, right? And from the negative standpoint, it's going to look like this, right? So this is what that looks like, and it's clearly not linear. So that was wrong. Now, but what are other conditions of linear systems? Well, there's this idea of homogeneity, right? So that's this. That means that, and again, looking at this system, if you say a constant, let's say that the new input is a times x into the system, same f of f, the output should be a times y. That means it's a homogeneous system, and whatever that is, the output should have the constant multiplied by it. It may be complicated, but still that constant carries through. Okay? Then additivity. Well, if you have x1 plus x2 going into the system, again, same system, mathematically or what have you, however you define it, the output should be y1 plus y2. That is assuming that the input, when you have x1, your output is y1, and so same thing for x2, giving you y2. Then if you add them together, you should get y1 plus y2 on the output right here. Okay? That's this additivity condition. You can go back to some of the equations, expressions I gave you on your homework and do this and prove to yourself that this is correct. The last condition is something called shift invariance. Now, what that means is that it doesn't move around with the function itself. So this is what I mean. If you said x plus s is the input, then you should get, again here, you should get y plus s. So this implies a shift in the placement. Now this, is a constant, but this implies a shifting in position. That shifting in position should be evident in the output of the function itself. So this again is another condition of linearity. So you give the properties of linearity so that now when you say nonlinear, that means everything else, right? Everything else that doesn't conform to these conditions is nonlinear. And that can follow a whole host of things. There are smooth nonlinear expressions. There are piecewise linear, nonlinear, and linear expressions. But if it does not follow these conditions, then this would be a nonlinear system. And thus, based upon our conditions, it could possibly be, or it could be a candidate for chaos. Okay? But again, you got to have these other things in play also for chaos. Now, so I want to take all of this and something that I have you looking at in the homework. I want to take that and apply it to something. Now, this map is a logistic map. Is called. Well, this was birthed out of a predator prey model. Meaning, if you have a environment that's populated with, I guess, prey, right? And here's predators, and that you could assign some ability for these prey to multiply, as well as the impact on the predators and what they do as far as, and I'll use my red again, eliminating prey, right? So there's an addition and there's a subtraction that happens because they're multiplying, right? But they're also being eaten. And a simplified model for it would look at the number of let's just say now, let's call X the number of prey at any given time in, any moment, any iteration at any point in, and you can just keep looking at that. So at X1, then X2, X3, so on to X, 1 million. What is that going to look like? Does the number run out? Does the number expand exponentially or something in between? Well, here's the expression that was derived. After people studied this, this is what was derived. So this X of n plus 1 equals this factor rho times X of n times 1 minus X of n. Now, you can see that this is nonlinear in that when you multiply this out, and let's just do that. So this is rho times X of n minus rho times X sub n squared. Now, so this gives you the next point. So let's just start off, for example, if I start off, so here's X of n, here's X of n plus 1. Okay, so let's just start off at easy number. 0 is going to be 0, and if you have no prey, you don't start. There's no reproduction, so it's 0. So that's a simple value. But let's just use 1, right? Easy to multiply. All right, so 1 times, so that's row, so 1, 1, but that's row minus row, and that's 0. So 1's not a good place to start either. Let's use 2 just so that 1 is easy to calculate, and 2 it's something that we can figure out. All right. So here, row times 2, and that's 2 row minus row squared, which is 4. So 2 row minus 4 row is minus 2 row, right? Then that goes into the next one. And that will, so then it'll be 2 minus 2 row, and you can do that. Continue going forward. Now I didn't want to put a value on row for a specific reason, which we'll get to in a second. But the point is that this determines what you get out next. What you get out next. Now, therein is the feedback. So we already had the nonlinearity, right? And that's, with here. Then you have the feedback, which basically says that the next value gets the previous value. So there's your feedback. And then the stretching comes with this multiplication factor of the number, as well as what happens actually with the x squared stretches it, but the factor row. So you have the stretching in the folding that happens in there. So the other part, just the fractal nature, we haven't seen yet, but that's only when it becomes chaotic. And this is not always chaotic. There's places where this is chaotic. Okay? Now, before I show some other interesting features, I wanted to go a little further with this. So we have, let's just say that, just for the sake of making this a little more manageable, let's say that y is equal to x n plus 1. And then we can say x is just equal to x sub n. All right, is that okay? Well, now we have y equals rho x minus rho x squared. Okay, so first of all, let's find out where the midpoint of this map. Now, what I did not do was draw it. This is a parabolic map. Let's see if we can figure out what it is supposed to look like. So here's x, here's y. So let's find out, first of all, where is y 0? Well, first of all, at 0, if we plug this in at x equals 0, we know that y is 0, so we know that. But let's also figure out where y is 0. So that means where y is 0. So if we said rho x minus rho x squared equals 0, actually putting it in that form I had before is better. Let's just say rho x 1 minus x equals 0, we know that we can solve this to say that, one, we know that x equals 0 is one of the solutions, which we know because we plugged it in and we saw it. But the other one is 1 minus x equals 0, which says x equals 1. So at x equals 1, we know that this is also 0. So now the question is, does this map go up like positively or negatively? Well, we can figure out where that point. Remember, we picked where's the peak of the peak or trough. We can find that out by doing a differential differentiate it. So we said dy dx is going to be equal to x minus 2x. And, well, rho, right? Rho is in there. So, but now we're going to set that equal to 0. Well, hold on. I'm wrong. I don't even know my own differentiation. All right, so I differentiated that again. It's going to be rho, because the differential of x is 1, with respect to x, is 1. So minus 2 rho x. That's the differentiation of dy dx. Now we set that equal to 0. We can get rid of the rho. We're going to have 1 minus 2x equals 0. We then solve that for x equals 1/2. Okay? And so we know at 1/2 we have a peak or a valley. Now, the easiest way to just figure out what that value is plug 1/2 back in. So let's say y equals 1/2. No, I'm sorry. Y equals rho times 1/2 minus rho times 1/2 squared. Then we'll know this is rho over 2 minus rho over 4, which is going to be equal to 2 rho minus rho over 4, which is going to be rho over 4. So we know that the peak is at this value, and for whatever rho is, we know that it's the peak. The value is going to be rho over 4, and we know it's a parabola, so it should look like that. Okay. So that's how you figure out what your map, at least what that map looks like. Now, these values of rho, which can take on different things, how does this map behave when you change it? Well, here's a interesting way. You've probably seen it if you've done any reading, investigation on this. I just pulled this from offline. As you can see the link there. But what's going on here? Well, here's a value. It's called R on this, but rho is the value. Here's the point where it settles. Remember we plugged in 1, and 1 gave you 0. So 1 for R is way. No, I'm sorry. That's the x value. For the rho value, where does it settle? Well, This is basically saying that if you make rho a certain value and then you start to iterate this, where's it going to land and stay? So this is very interesting. As you start turning up the number on this, you get the values, the settling values start to go up at 0.6. And then right about here, a little bit beyond 3, or maybe right at 3 or so, the value that it settles on splits. So meaning that the settling value just kind of bounces between 2. And it keeps doing that even as you go a little further. You make rho equal to 3.4. Here's where it, so it's going to settle on these 2 places, back and forth. And you can try this, and I'm going to, as we get our MATLAB function ability, we're going to play around. We're going to see this, right? See it stick on 2 values and just keep going back and forth, back and forth. In time, you'll see it look, or I say an n, right? It's going to look something, just like this. There's going to be some value here. It's going to go back and forth like that. Now, but what happens as you go a little further, it splits off into 4. This one, this one, this one, this one, and so on. And as you could keep looking, it splits to 8 and 16 and so on. So this is what's called a period doubling. And this ultimately leads to chaos, and the chaos, quote unquote, is what these really highly dense areas are, because they're not fixed on say, it doesn't just jump to from 16 to a million. It's all over the place. And how you know that this is not just a continuous doubling of 2, 4, 8, 16, 32, 64, and so on. The reason why it just doesn't just keep doubling forever, and these aren't just doubles, because right here is a period 3, which means there's 3 points that it settles on, and that can't come out of this root. So it has to be something else going on that creates a period 3 type of action that comes out of here. So I definitely encourage you to read more on this. There's a lot of fascinating things. There's something called the Feigenbaum number. And one of the next homework questions, not numbers. In the next homework question, I'm going to ask you to find out what this is and to describe it to me, and even perhaps show how you would calculate it. And it's one of these things that's a limit, but I want you to investigate it. I want you to look at it, and you tell me. So that'll be in your reading and searching, and all you have to do is search on that. You'll get more than you ever wanted to know about it. But it's very fascinating. It even like one of these universal constants that shows up in things like this. And this remember, this comes from this single humped map, the logistic map, but you'll find that this type of bifurcation, and I never really said that, but this is called a bifurcation diagram. You're going to see this show up all over the place. Okay? Now, last thing I want to do before we end today is I want to just talk about dimension of a fractal and how you would calculate it. And then I will have you then calculate dimension for some given fractals that I provide. But I want to show you that. Now, the calculation is this. D equals the log of n over the log of, I don't want to use, I'll use R, but R is not the same R as what you saw before, what we were talking about before. So n is the number of elements, and R is the multiplication factor multiplication, forgot how to spell, factor. Now what is a multiplication? It means, it actually is how small the units is shrinking. But all right, let's look at an example first in two dimensions. So the first one is, all right, let's just have the box. And let's just say this box is, of unit length, 1, 1, 1, 1. And if you want to be able to say, calculate the area, then it is the, let's just call this the base and the height. Okay, but we know that's 1. That's 1, and that's 1. Okay, so if we wanted to break this up, the pieces, equal pieces, and now, so the first one is the log of 1 over the log of 1, and that's 1. But that's not very interesting. Here, you're going to have 4 pieces, so 1, 2, 3, 4, and so n would be equal to 4, and the length or the area, whatever you want to call it, is so now this is 1/2 and that's 1/2, so the area of that is 1/4. And so then this would be the log over log of 4 over 4. Or you actually just look at the length. So the log of so log of 4 over 4. Now let's look at the example with. Let me clear this out. I got a meeting coming up. Let's look at the. Let's first look at the what we call the Cantor set. So this is first iteration and it's length 1. So now this is the next iteration. There's 2 elements, but their length is this is 1/3. Okay, and now if I did it again, so it's 1/3 of 1/3, but you have 4 elements here, and it's a third of a third. So this is 1/9 length. Okay? So here you can see that the dimension, I use capital D, is equal to the log of 4 over the log of 9, because it's one, the multiplication factor is 9, so it's 1 over that. So you can see that this number, this denominator is bigger than the numerator. So this is less than 1. So it's a fractional dimension. So that's one example. And you can do this in just about any form or fashion. I'll have another example for you next time. I don't want to run too long on this, so we'll stop right here. But I want you to also look at examples of how to calculate the log or calculate the dimension of fractals. I want you to be able to discuss it on our next discussion session. And also, I want you to be able to talk about the Feigenbaum number and bifurcation diagrams and the single hump map. I'll also show you what, next time, a map that looks like it is linear, but it's not. And we'll investigate that. And then I'll show you how to get a relationship between the map and a real time, not real time, but a 3-dimensional chaotic flow, okay, or state space. And I'll show you how to link the state space to a map, and a map to a bifurcation diagram, and all this stuff will be connected together. And we'll do that. I'll go through and show you how to take a higher order differential equation, turn it into a system, and then the system is what allows you to create a state space that you can then look at from a chaotic standpoint. Okay? All right. I know it sounds like a lot, but we're going to walk through this slowly. You get all the principles down, and should be able to have a good time with it. All right? So that's where we'll leave it right now. I am looking forward to continuing to talk about this with you. And if you have questions, reach out to me via email, or we can have at our next chat session, we can talk through it. Okay? All right. Have a good evening.